Hello there, Mr. Sutton here, bringing you the AB Calculus 6-1 Extra Practice Number 2 solutions on differential equations in one variable. On this problem, we just need the general solution for this differential equation. So basically, we need to take the antiderivative of both sides. I'm going to rewrite this as x to the negative fifth, and then I'm just going to use my reverse power rule. So this bumps up to a negative 4. Dividing by that, I have y equals negative 1/4 x to the negative fourth, and then don't forget the plus c. For this one, we need the general solution for this differential equation. So taking the antiderivative of both sides then, we end up with y equals negative 3 cosine of x plus c, and that is our general solution. On this problem, I want the particular solution for this differential equation with this initial condition of y of 2 equals negative 3. So first I have to get the general solution by taking the antiderivative. So that'll be y equals, reverse power rule, we have negative 2x squared plus 3 plus a c. And now if I plug in the x value 2, I should get back a y value of negative 3. So I've got negative 3 going in for y, 2 going in for all these x's, and now I just have to solve for c. So this is going to be negative 8 plus 6, which comes out to negative 2. If I add the 2 over here to get c by itself, I have c equals negative 1. And then plugging that back into the general solution, we have y equals negative 2x squared plus 3x minus 1. For this one, we're trying to find the particular solution for this differential equation. So we'll start by taking the antiderivative, and I think we can make our life a little bit easier if we rewrite this as negative 3x minus 1 to the negative 2 power. And now I can use my reverse power rule. So this bumps up to a negative 1. Dividing by that, this becomes a positive 3, x minus 1 to the negative 1 power. And now let me just plug in my initial condition. Oh, wait, have a plus c. All right, now let me plug in my initial condition to figure out what that c value is. So if I plug in 1/4 for y, that's going to equal all this stuff with negative 3 plugged in for x. So I can rewrite this as 3 over negative 3 minus 1. And then we still have that plus c there. So this is going to be really 3 over negative 4. If I add 3/4 over here, that's just going to be 1 for my c value. So that kind of works out nicely. And then just rewriting this again, I can write 3 over x minus 1 plus 1. On this problem, I'm trying to find a particular solution for this differential equation with the initial condition given here. Let me start by taking my antiderivative to find the general solution. So that's going to be y equals 3 ln absolute value of x minus 3 plus c. And now let me plug in my initial condition to figure out what that c value is. So if I plug in the y value, 3 ln of 5 minus 3. So this is all one big y value over here. That's what I get if I plug in the x value negative 2 inside here. So this is really 3 ln of positive 5 after we apply that absolute value. If I subtract 3 ln of 5 from both sides, then I'm just left with negative 3 on the left side and c on the right side. So c is negative 3. Now, plugging this back into my general solution, I also have to resolve this absolute value. To do that, I look back at my initial condition, and I see that my x value that I'm plugging in is negative 2. Well, if x is negative 2, then this x minus 3 stuff in here is going to come out negative, which means I need to force the stuff in here to come out positive by negating all of the stuff inside absolute value. So to write this without absolute value, which I have to do, I'm going to rewrite this as negative x plus 3 inside of parentheses. And now I can't forget I have that c value that I just found of negative 3. On this problem, I want to know which of these is the solution to this differential equation. So I'm not really sure how to solve this differential equation just kind of on its own merits, but I have all these possible solutions. To figure out which one is the true solution, I can verify it's the solution by just plugging it in to this differential equation. Now the catch is when you're plugging these in, I mean obviously for y I'm going to use whatever y equals here, but there's also a y prime where I have to plug stuff in, so I'm going to have to figure out the derivative, the first derivative of whatever I'm plugging in. So let me start with choice A. y prime on that is just going to be 2x. So plugging y and y prime into this differential equation, I've got x times 2x, because that's what we just said y prime was, minus 3 times y, so that's 3 times x squared plus 2, and all that should equal 6. Now let me do a little algebra and see if this actually works out. So we have 2x squared minus 3x squared minus 6. And doing a little simplifying, I have, let's see, negative x squared minus 6 equals 6. And this might be true for some x values, although I'm not even sure about that. If I add 6 over here and divide by negative 1, I'm basically trying to square root of negative numbers, so that's just outright false. But even if it did work for certain x values, this has to work. This equation has to be true for all x values for it to count, for this to solve the differential equation. So because it doesn't work for all x values, or really any x values, this is a no, and we're going to move on until we end up with the same thing on both sides of the equation after simplifying. Now for this next one, my y prime is 6x. So plugging that in, I have x times 6x minus 3 times 3x squared minus 2. All of that still equaling 6. So we have 6x squared minus 9x squared plus 6 equals 6. And this is, let's see, negative 3x squared plus 6 equals 6. Same deal as up here. Even if it did work for some x values, it has to work for all x values. Really, we don't want any variables when the dust settles here. So this is going to be another no. And let's keep going. This one, we have a y prime of 15x squared. Plugging that in, we've got x times 15x squared minus 3 times 5x cubed minus 2, all of that equaling 6. So this is 15x cubed minus 15x cubed, so that's a good sign. And we have a plus 6 as well, equaling 6. These 15x cubes are going to cancel out, so we just have 6 equals 6. And that is an emphatically true statement, so this is a yes. So this is probably our answer, but let's just check this last one to be on the safe side. So y prime here is going to be 21x squared, so we have x times 21x squared minus 3 times 7x cubed plus 2. So that's 21x cubed minus 21x cubed. So far things are working out. And we have a minus 6 equals 6. 21x cubed cancel, but negative 6 does not equal 6. So that's not true for any x values. So that's a no. So that just confirms what we thought, which was that answer choice C is the one we want. On this problem, we have this differential equation, and we want to know which of these solutions is the actual solution to this equation, and it could be more than one of them. So to figure this out, all we have to do is figure out y and y double prime. We actually already have y. We just need y double prime, and then we plug in the original function along with y double prime to see if it makes this equation work out the way it should. So for the first one here, we first need y prime. Using our chain rule, that's going to be 6 cosine of 2x. And then y double prime using another chain rule is going to be negative 12 sine of 2x. So plugging that in, we've got 4 times the original function. So that's 4 times 3 sine of 2x plus y double prime, which is just this stuff right here. And does that come out to 0? Well, this stuff over here is really 12 sine of 2x. So if we subtract 12 sine of 2x from itself, we do indeed get 0. So that's a yes. Option 1 works. So anything that doesn't have option 1 is out. So choices B and C we can already eliminate. And now option 2, we've got a y prime using our chain rule of, this will be negative 10 sine of 2x. And then y double prime with another chain rule, we've got negative 20 cosine of 2x. Plugging that in, we have 4 times 5 cosine of 2x, and then plus that y double prime, that's negative 20 cosine of 2x. This is 20 cosine of 2x minus itself, which gives us 0 on both sides, so this is a yes. So it's looking like choice D. There is no option for 1, 2, and 3, so we're pretty much guaranteed that this third option is not going to work. But if we want, we can just check it out just to see what's going on there. So y prime for option 3 would be 2e to the 2x. Y double prime is 4e to the 2x. So we've got 4 times that original, 4 times e to the 2x, plus this y double prime of 4e to the 2x. And if this were a minus, we would actually have 0 over here, but this ends up being 8e to the 2x because we're adding instead of subtracting. So that is not going to be the same thing as 0. In fact, this isn't even one of those, it doesn't work for all x values situations. This won't work for any x value. An exponential function is guaranteed to come out positive as long as you don't have a negative coefficient. Certainly it can't be 0. So this is an emphatic no. So we have to go with options 1 and 2, which is choice D. For this problem, we want to know out of these choices which is not a solution to this differential equation. So the way this is worded, that means 3 of these will be solutions and 1 will not. All right, well, to figure out if something's a solution to a diff EQ or not, we need to, one way to do it is just plug it in. Now, plugging into this differential equation means we need to know the y prime and the y triple prime for each of these options in order to plug those in to this equation. So let's start with the first one here. This is the easiest by far. Y prime of 10 is just going to be 0. Y double prime of that is going to be 0. And y triple prime, you're taking the derivative of 0 over and over again, so those are all going to come out to 0. So plugging all that in, we have 0 plus 4 times, well, this is a different 0, but it's still 0. This is y prime 0 instead of y triple prime 0. Still 0, though. So we have 0 plus 0. Everything is 0. Everybody's happy. This works. I'm going to say yes here, but what I really mean by yes is this works, so it's not the answer choice we want, because we wanted a solution that did not work. So let's move on to the next one and see if we can see if this one fails. So y prime on this, that's going to be using my chain rule, negative 8e to the negative 2x. And then y double prime, we have 16e to the negative 2x. And then finally, y triple prime, negative 32e to the negative 2x. Plugging that in, we have our y triple prime, which was this negative 32e to the negative 2x that we just got, plus 4 times y prime. So that's 4 times negative 8e to the negative 2x. And we're trying to see if that equals 0. So this is going to be negative 32e to the negative 2x plus the other negative 32e to the negative 2x comes out to negative 64e to the negative 2x, which, because it's exponential, cannot have a value of 0. So this is false. Since that doesn't work, this is actually the one we're looking for. We were looking for the one that was not a solution, the one that does not come out the same on both sides. So let's just go with choice B then. For this problem, we're trying to figure out which one of these particular solutions solves the differential equation sine of x squared and with this initial condition over here. So one way to do this is if you actually knew how to take the antiderivative of this thing, plugging in this initial condition, finding the c value, and seeing which one of these it came out to. Unfortunately, we don't really have the mathematical equipment to do that. So what we're going to do is kind of the next best option, which is to take derivatives of all the answer choices until we get something that matches this dy over dx. And if we get more than one match, then we start plugging in the initial condition to see, if that actually gives us 4 when we plug in radical pi. So let's start with our derivatives. So this first one, choice A, this derivative, this is going to be, let's see here, sine of x squared, which is a good start, but we have to multiply by the derivative of x squared because this is the chain rule. So that's times a 2x. And I mean, that's already not the dy over dx that we wanted. So that it gets eliminated pretty quickly. Then we have this next one. So this is kind of a mess, but yeah, this is going to take the, this is going to require the quotient rule, this one. So I think this is one of those where you come back to it. Yuck, let's try the others first. Yeah, let's come back to this one if none of these other ones works. If we can eliminate these, then we'll just pick B and call it a day. But let's see how these other ones go. So taking these derivatives, for both C and D, they're pretty similar. We've got these constants 4 out in front, which are going to be zeros, so that's okay. Now we're taking the derivative of an integral with a variable in the upper limit. So this actually is going to use our fundamental theorem. We're essentially going to plug in that upper limit for the dummy variable in here. So for C and D, you're going to end up with sine of x squared for both of those derivatives. Since we have something that matches for two different answers, we're going to go to the next option, which is plugging in the initial condition. So if I plug radical pi in, I should get an output of 4. Let me try that on this first one. So this would be 4 plus the integral from 0 to radical pi of sine of t squared dt. Now, here's the issue with this one. I don't know the antiderivative of sine of t squared. I mean, if I did, then I could have just solved this the normal way in the very beginning, right? And I need to know the antiderivative if I'm going to evaluate this thing from 0 to radical pi. So I have no idea what this actually comes out to. But I'm going to guess it doesn't come out to 4, but I don't really know. So I'm going to say question mark for now. And I'm really going to hope that I get some clarity on choice D, because right now between B and C we've got two options that we were not able to eliminate. So for choice D, y of radical pi, we're going to be going from radical pi to radical pi for the limits of integration. And this is actually a very good thing. Since the limits of integration match, that means you're going to automatically have an area of 0 for that integral. So we just have 4 plus 0, which is just 4, which is exactly what we wanted. So our initial condition matches, our derivative matches. I say we go with choice D.